First of all, I just want to start by thank you for the introduction and for the invitation to speak at this first ZULF NMR meeting. And what I'm going to be talking about today is the work we've been doing in my group over the last few years on developing an in situ method for looking at SABRE hyperpolarization using Earth field NMR for detection. So as we are all well aware, the vast majority of NMR that is done around the world is done using laboratory NMR spectrometers with high field magnets that are made using superconducting magnets. But that there's been an emerging field in recent years on pushing towards more low field and portable instrumentation. And usually when I give these talks at NMR meetings, I sort of highlight the different regimes and talk about my work in the Earth field as being sort of ultra low field NMR. But of course, it's fun to be at this meeting where my Earth field work is just a little bit high field compared to the rest of you guys. So one of the things that I find most remarkable about the idea of using the Earth's magnetic field to do NMR is really how old of an idea it is. And what you can see here by this paper by Packard and Varian from back in 1954 is that they showed that Earth field NMR was possible within sort of the first decade of NMR being discovered in itself. And so what you can see with this very brief report that they wrote, they saw the Larmor frequency of protons in water to be about 2000 hertz in the Earth's field, and they even looked at a sample of HF and saw the beat frequency that came from the difference in Larmor frequency between hydrogen and fluorine, which is about 120 hertz in the Earth's field. The other thing I want to highlight about the work that they did is that in order to get signal in the Earth's field, not only did they use a large sample of water, but they also used a prepolarizing field of about 100 Gauss, so that's about 10 millitesla. And so this just goes to show that when you're doing NMR in these very low fields, that often some form of prepolarization or hyperpolarization is needed in order to make them work. And so what I want to focus on today is how we can do complementary work in ultra low field NMR and looking at sensitivity issues. So if you break down NMR sensitivity into the various factors, we've seen a lot already at the conference about detection sensitivity. So we know if we're using inductive detection that that's very inefficient at low fields and low frequencies, and so you can swap to using more sensitive detectors. But what I'm focusing on here is the idea of polarization. So the sensitivity or the signal we get in NMR is going to be proportional to this very small population difference between our Zeeman energy levels, so to our polarization. And so the idea of hyperpolarization is to say, well, what if we can force our system out of equilibrium into a situation where we overpopulate one of these energy levels, and so we create more polarization. And clearly there's a potential to get gains of many orders of magnitude because the polarization that we have at thermal equilibrium is in the ppm range. So if you're going to think about using hyperpolarization in conjunction with low field or ultra low field or ZULF NMR, and your sort of goal is to have compact or portable instrumentation, then you have to keep that in mind when you're choosing a hyperpolarization method. You want something that is flexible and relatively low cost and easy to implement. And that's why we've seen, I think, a great interest in recent years on using parahydrogen-based hyperpolarization with ZULF and other low field techniques. So what is parahydrogen? So parahydrogen is a nuclear spin isomer of a molecular hydrogen, so of H2. So if you think about H2, we basically have two protons, each of which are a spin half. But because of the symmetry of H2, we can't distinguish between them. We have to think about them combined into a single state. So we can think about them combining to create a triplet state with spin 1 or a singlet state with spin 0. So that's orthohydrogen and parahydrogen. And due to the particular symmetry properties of molecular hydrogen, there's a coupling between the nuclear states and the rotational states. So that means that there's actually quite a significant energy gap between these two manifolds. And parahydrogen is the lower energy state, and so it will be preferred at lower temperatures. The other key important point here is that there's a difference in symmetry, and so therefore the transitions normally between these manifolds are as symmetry forbidden. So if we can enrich our hydrogen gas in the para state, then it will remain locked in that state for potentially a long period of time, weeks or months, because it is very slow to come to thermal equilibrium with orthohydrogen. So how do we enrich hydrogen in the para state? Well, what we need to do is we need to create a situation where we can have transitions between parahydrogen and orthohydrogen. So we do that by exposing it to a paramagnetic catalyst. So we flow hydrogen gas into a coil which is packed with something paramagnetic like iron oxide, and then we cool this block down to a given transition temperature. So if you think about what percentage of parahydrogen we would expect to have at thermal equilibrium at given temperatures, at high temperatures about 25%, and then if we go down to liquid nitrogen temperatures, it would be 52%, and if we go down below 30 Kelvin, you would get better than 99%. So the idea is that we cool this coil down. The hydrogen is in contact with a paramagnetic catalyst, so we get rapid equilibrium at the given transition temperature. So we enrich the hydrogen in the para state, and then as we take out the parahydrogen enriched gas, we isolate it from the paramagnetic catalyst, so it's no longer in contact with it, so that when we heat it up, it remains locked in the parahydrogen state. So this gives us a fairly easy way to basically have parahydrogen on temp. And the things to remember about parahydrogen is it has no overall nuclear spin, so it's NMR silent, and because it's essentially in a pure nuclear spin state, it has this potential to generate hyperpolarization, but that needs to be sort of unlocked through the use of a chemical reaction. So there are two basic modes of doing parahydrogen-induced polarization. We have the hydrogenative mode, and I believe that Stefan in the next talk will talk a lot about that. But what I want to focus on is the non-hydrogenative version. So this is SABRE, for signal amplification by reversible exchange. So the idea behind SABRE is that it's a catalytic process for transferring the polarization from parahydrogen-derived protons to a target molecule without changing the chemical identity of the target molecule. And that's done using a reversible exchange reaction. So what does this mean in practice? Well, in this sort of cartoon view that I'm showing here, we have a metal complex, and it binds a molecule of parahydrogen to form these two hydrides, and it also reversibly binds one or more molecules of what we call our substrate. So that's the molecule we're trying to hyperpolarize. And then we have an excess of the substrate in solution, and we're constantly supplying fresh parahydrogen. So if you imagine our NMR tube, we have a solution with the metal complex and the substrate. We add parahydrogen as a gas, and then we shake the tube for the gas to go into solution. So it binds to our metal complex. So now we've broken the symmetry between the two hydrogens from parahydrogen. And so under the correct conditions of magnetic field and J coupling, we'll have a spontaneous transfer of hyperpolarization from the hydrides to our target substrate. And remember, I said that the substrate and the hydrides are reversibly bound, so we can have exchange events where the hyperpolarized substrate exchanges into free solution, and we have sort of a refreshing of hyperpolarized hydrides through exchange of parahydrogen. So this is happening over a period of time. So if we are shaking our NMR tube for a period of a few seconds in a suitable magnetic field, we build up polarization on our substrate in free solution. We put our sample into the magnet and we detect the enhanced response. And we can get hyperpolarization levels by many orders of magnitude using this process. So if we think a bit more about how we're carrying out this experiment. So here I have a little video to show you what it looks like in practice. I think I need to get rid of my pointer to make this work. Oh. That's unfortunate. I cannot play my video. Oh, there we go. Sorry. Okay, so in this video, Olga, who just recently graduated with her PhD from my group, is doing a SABRE experiment where she's shaking her NMR tube outside the magnet to generate the hyperpolarization. Then she puts the sample into the magnet to detect the response. So basically, this is a two-stage process where we have hyperpolarization transfer by SABRE in the ZULF regime outside of the magnet, and then detection in the high field regime. So this is kind of an ex situ approach to doing SABRE. So what I was interested in is trying to explore what's happening in the ZULF regime directly. And so what we want to do is we want to do an in situ experiment where we're actually carrying out the hyperpolarization and the detection in the ZULF regime. So we don't have this sort of transfer step where this is very much a black box. So to do that, that's where our detection using the Earth's magnetic field comes in. So the requirements for the system that we want to develop are that we have a relatively large sample volume and an open bore. And this is because what we have is a reaction chamber where we're going to bubble parahydrogen through a solution. And that's contains several milliliters of samples. So we're not working in an NMR tube, we're working in this reaction chamber. So we need some space in our detector for that. We want to be able to access the full range of ZULF fields from sort of 0 up to 20 millitesla. And we're going to do this in a field cycled way so that we have a common detection regime. So while we may change the polarization transfer field where SABRE is happening, we're detecting in the same way for each experiment. And ideally, we want inexpensive and flexible instrumentation. So choosing to use the Earth's field because it's freely available, and since it exists anyway, if you want to generate your own field, you first need to get rid of the Earth's magnetic field. So just using the Earth's field means we don't have to do the shielding, or sort of passive shielding. The Earth's field is relatively homogeneous over large samples, so simple first order shims can give us very nice line widths. Instrumentation is relatively simple and inexpensive, and you can buy commercial Earth field NMR spectrometers that have an electromagnet already built in, which we use for prepolarization. So that's for accessing the sort of millitesla range polarization transfer fields. And here we've got a lot of signal from the hyperpolarization, so we're using inductive detection, and that's helpful in terms of having this sort of open geometry, although you know, where you're giving up a lot of sensitivity because clearly an inductive coil at these types of frequencies is not very efficient. So to do these experiments, this is sort of a cartoon of what our system looks like and a photo of what one of our actual reaction chambers looks like. So hydrogen comes in and is bubbled through a frit, and when we have a solution in here about 4 or 5 milliliters, and then there's a second outlet here for the exhaust. The flow of parahydrogen through the reactor is controlled by this polarizer, which also connects to our parahydrogen generator, and the reactor just sits inside the detector coil for the Earth field NMR spectrometer. We have a very basic pulse sequence. We're bubbling parahydrogen throughout. We turn on the polarization transfer field, so say 6.5 millitesla. We build up polarization through SABRE, and then we switch that off to adiabatically and detect in the homogeneous Earth's magnetic field. And so we'll get a result that looks something like this. We have a frequency around just over 2 kilohertz. So this is polarization transfer to protons at 6.5 millitesla. The sample here is pyridine with our catalyst in methanol. And what we can see is that we have a very nice intense peak, and also that it's a relatively narrow line width, so sub-hertz line width. But it's just a single response because in the Earth's magnetic field, we don't have chemical shift resolution. So in the absence of heteronuclear couplings, we just get a single peak for each type of nucleus. So what can we do with this type of system? So one of the things we've been looking at is the activation of the SABRE catalyst. So to do SABRE, we have this active catalyst that binds multiple molecules of our target substrate. Here's pyridine, and the parahydrogen is bound and forming these hydrides, and we have a stabilizing carbene. But we don't start off with the active catalyst. It's air sensitive and particular to your substrate, so we actually start off with a pre-catalyst, which we mix with the substrate to form our complex 2 here, and then we bubble parahydrogen, which forms this dihydride intermediate, which undergoes ligand exchange to form our active catalyst. So on this time course here, in our first dot here, our first experiment, we've injected essentially a solution of 2 into the reaction chamber. We start to bubble para-hydrogen, and we build up signal as we're forming the active catalyst. And then we reach a steady state once the catalyst is fully converted, and we have a very reproducible response. So this allows us to probe the catalyst activation, but also just shows how we're getting a very reproducible response, which allows us to really look in detail at the SABRE process. So in the experiments I've just shown, we just have a single response for protons, which because we're dominated by the Zeeman interaction and have no chemical shift, is just a single peak. But if we can introduce heteronuclear couplings, then we'll break the magnetic equivalence of our nuclei, and then we'll get much more complex peak patterns appearing in our spectra. And these are characteristic of the underlying spin states. And it's particularly convenient to use proton and fluorine because they're only 130 hertz apart in the Earth's field. So the model substrates that we've been looking at are different fluoropyridines, in particular the one shown here, where we have a lot of fluorine and a certain amount of symmetry, which simplifies the peak shapes. So by using systems where we have these heteronuclear couplings, then we can extract additional information from our Earth field spectra about not just how much hyperpolarization we're getting, but what states are actually being hyperpolarized. So there's just a quick example here of that, where if we hyperpolarize at 6 millitesla, where we would expect optimal transfer to proton, we get both proton and a fluorine response. And if we do it just in the Earth's field, we get no proton, but we do get a fluorine response, but it now looks very different. We're very much hyperpolarizing a different state in the Earth's field transfer. So to fully explore this, we want to not just go down to the Earth's field, but below the Earth's magnetic field. So to do that, we're doing active cancellation of the Earth's field using a set of 3 Helmholtz coils. So we have an X, a Y, and a Z coil to produce fields in all 3 axes. So we start by just orienting this whole apparatus such that the Earth's field is in the YZ plane. Then we can apply a small field along the y-axis to counteract the y component of the Earth's field. So our effective field is along Z. And then we can use the Z coil to adjust our effective field to either increase it along Z or decrease it along Z. So now we have access to full range of fields from 0 all the way up to the sort of millitesla regime. And just to show you that this works quite well, once we have applied this Y correction, we get a very linear response between our Larmor frequency and the current through the Z coil. So that's just showing that our effective field is very much along Z. And crucially, even when we're doubling the Z component of the Y field, so we're going from 1500 hertz to 3000 hertz, we see only a very small increase in line width over our very large sample. So that's just showing that the homogeneity of this field that we're adding is quite good, even with just a very inexpensive power supply being used to generate it. So if we revisit the setup I showed at the beginning from our early experiments, we will now have the ability to make more sophisticated measurements. So instead of just doing an increase in field for our polarization transfer field, we can cancel out the Earth's field. But the way this particular setup worked, we couldn't interact between our spectrometer, which is controlling the pulse sequence, and any external elements of our system. So our bubbling is starts and stops outside of the pulse sequence, and we would need to, and we want to be able to interact with other things during the pulse sequence. So that's been some recent work that's being done by Fraser Hill Casey in my group, building a more flexible and modular system for the in situ SABRE. So here what we have is the spectrometer that's running the Earth's field NMR. We can embed TTL pulses inside the pulse sequence that then trigger an Arduino that controls things like the para-hydrogen generator, our flow system, and these external coils for field correction and RF shielding. So this is going to give us the flexibility to really explore the full parameter space within our pulse sequence with more controlled timings. So just to conclude and provide a bit of an outlook for where we're going, I think that SABRE is a really promising method for signal enhancement for many applications, and that this comes from the fact that it's quite quick. It provides hyperpolarization quickly. The hyperpolarization is renewable. You can, once you give fresh pair of hydrogen, you can repolarize the same sample. The level of polarization is independent of your detection field, and it's relatively cheap and easy to implement. But despite the fact that it's quite easy to do a SABRE experiment, it's quite challenging to optimize it. And so that's what we're really aiming to use this in situ detection for, is to better understand what's happening in these experiments and how we can optimize them for a wider range of analytes and experiments. And just to finish by thanking members of my group, particularly Fraser and Mathis and Emanata, whose work I featured today. A lot of this work is done in collaboration with Simon Duckett here at York, and also thank you to funding agencies.
All right, thank you. And that was a beautiful talk. We have actually a number of questions. So Daniel Barsky asks, in your setup, do you have a problem of the liquid going back into the line through the frit when parahydrogen flow is stopped?
No, so we have a number of one-way valves to control the flow to make sure that there's no backflow. We certainly have points where there's been a failure somewhere, like one of the valves has failed, and then suddenly your sample disappears, and then you can destroy some of the parts if you get the solvent going the wrong way. But we have quite a few one-way valves to try and prevent that from happening on routine use. Yeah.
Yeah, but this is really funny that your sample is lies on its side. It's probably one of a few examples. Okay, then there is another question. Are there any volume effects on SABRE catalysis by using much larger sample volumes to examine SABRE polarization transfer at Earth's field than would typically be used for high field detection? Okay, so volume effects.
So I don't notice anything in particular, but it would be hard to perhaps conclusively say whether there were any effects. It's hard to directly compare, say, the level of signal you get in one instrument to another, and in the Earth's field, estimating levels of polarization is challenging because you can't just have a kind of unpolarized versus polarized experiment. I think that what I would say is that the behavior we've seen when we compared high field and the Earth's field in terms of changing concentrations and between substrates have all been very consistent with the same trends. So I haven't seen anything. There could be questions about, say, when you're bubbling, how effective your mixing is. So there may be some regions of your sample that are mixed more effectively and so are becoming hyperpolarized more effectively. But since we're doing an average measurement over the whole system, I don't think that there are any that the volume is playing a significant role there.
Okay. Okay, this is not question. Okay. There is a question from Raman Shipping. How the full spectrum of fluorinated compounds looks? I guess the question is about the lines of fluorine and protons. I guess.
So I mean, I'm just showing, yeah, so there's mostly just a whole bunch of noise in between the two peaks. But in these cases, because of the tuning range of the coil, what we usually do is we still do acquire two separate spectra where we tune to the two frequencies, or we by default tune to the fluorine frequency, just because the tuning range is only a few tens of hertz, really. So I suspect that these figures were produced by one of my students, but I suspect these were actually separate experiments. Yeah, so if you were to zoom out to the whole Earth field spectrum, so one of the weird things about the Earth field spectra that we acquire is that we we acquire from 0 hertz to 3000 hertz. We acquire everything in between. So it's like we're acquiring in the lab frame instead of the rotating frame. So these really are zoomed in because our spectral width is several kilohertz. And here we're looking at like 10 hertz. And the most notable feature of the Earth field spectra is that you get huge noise spikes at multiples of the mains frequency of 50 hertz. But otherwise, it's just these are zoomed into the only, signal peaks that are available, that are seen in the spectra. Yeah, so you would just have the one proton peak. Yeah, so you've got sort of on the purple side is the hydrogen, and it's split because of the coupling to the fluorine. So it's actually so it's split multiple ways. And then the fluorine again here is split in because of the couplings to the protons.
Okay, then there is a question from Michael Taylor. Can you describe your method for XYZ shimming? How long does the shimming process take, e.g. Number of scans and so on?
So basically inside the Earth field system that we have, they have X, Y, and Z gradients that are designed for doing some imaging, and we just co-opt them to do X, Y, and Z shimming. And the first time you set it up, it may take some time to do the shimming, but it's just like you would at high field. You just have an automated kind of shim routine. It's nothing like as sophisticated as on like a Brooker where you've got multiple, like several orders of shims. It's just 3 shims, so it's doing a very, naive kind of algorithm to step through the different values. The shim is relatively stable. I mean, the key to getting this to work is to have your probe quite isolated, so a few meters from the floor, a few meters from the wall, and make sure people don't move instruments or things close to it. And then once you've sort of isolated it, most of the inhomogeneity is linear, and so the linear gradients are enough to overcome it. But just like in other situations, if you start with a very far from a good shim, it may take you some time to optimize it. But
there is just Michael specified. He meant XYZ Helmholtz coils. So that means the offset of the field, right?
So that's very straightforward. So we just so if you have where's my picture here? Yeah, so our coil so the probe is oriented so it's along one axis of the threefold Helmholtz. So we start by just acquiring a series of spectra with different amounts of current in our X coil. So we're adding a bit of X field, and by mapping out so the Larmor frequency goes with the effective field. And so by doing a little bit of trigonometry, if you take a few points, you can work out what the angle is between the field you're applying, which we're calling X, and the Earth field. So that will tell you what that angle is. And we want it to be 90. So we just keep rotating until it becomes 90. And that, my students are very used to doing that now. So it probably takes about half an hour to do a few measurements and orient it. But because we're quite used to doing that. And then and again, you can check, now that it's oriented, we do a quick check with a couple points at the beginning of the day, make sure that it's not very far from 90, and then and do a quick fix if the direction's changed a little bit.
Okay. Then there is a question. Can you comment on the phase of fluorine-19 SABRE signals? On the phase. Okay, so it's antiphase, right?
Yeah. So what the antiphase is basically telling us, presumably, is that we're hyperpolarizing some 2-spin order term, like an IZ, SZ kind of term, where when you do your excitation, you get the antiphase component coming out, and so the idea is to use numerical simulations to sort of decode what's in the spectrum and understand what's being hyperpolarized.
Okay, Jessica asks, can you talk more about why go below Earth's field?
So if we want to, so in SABRE, in order for transfer to take place, we essentially need to bring the energy levels for the hydride protons, which come from parahydrogen, and the nuclei of the substrate. We need to bring them close enough together, their Larmor frequencies close enough together that the energy gap can be bridged by the J coupling. So the J couplings are typically on the order of about 10 hertz. And so if you're taking so the hydrides are at minus 23 ppm, and if you've got an aromatic, your protons are sort of 8 ppm, so you've got a 30 ppm difference. And so if you work out, you need a field of about 6 millitesla to bring those close enough that they're sort of a 10 hertz difference, so you can overcome that gap with the J coupling. But as has been shown by other groups, if you've got a heteronucleus, if you're trying to bring a fluorine and a proton together, then you're going to need to go to much lower field to bring their Larmor frequencies close together, because it's not chemical shift you're overcoming, overcoming the difference in the gyromagnetic ratio. And so if you plug those numbers in, you see that that's in a much lower field range. And so that's why you need to go below the Earth's field.
But I guess you cannot polarize the carbon-13 on N15 like that. You still need shields.
No, you could, in principle, you could. I just think you would struggle to detect it in the Earth's fields without using a magnetometer or something. But it's possible.
But if you polarize it and then quickly switch the field, then probably it would be. But you haven't observed that.
Well, we haven't. Yeah, we haven't tried that yet. I mean, certainly something we want to try. But you would. We're using quite big samples. And so if you're using labeled compound to test that out, it gets quite expensive quite quickly. So we're using fluorine to start with, just because it's easy. But in principle, if you were generating enough hyperpolarization, you should be able to see do it to other nuclei as well. Okay.
Probably I will ask one last question. There are actually still many questions, but one or two. Okay, there is a question from Peter Bloomer. Do you have a RF shield? Didn't see it. Should be thick at these low frequencies.
Yeah, so the first trick is that the electromagnet on the outside of the Earth's field probe is shorted during acquisition to form a quite extensive RF shield. So that's a very thick layer of copper. But we also, it's not in the pictures, but we have another RF shield on the outside that we do in addition, which is just a bunch of thick wire, again, that we also short during acquisition to further reduce. Because by far the main source of noise in these experiments is external noise.
Okay, then probably one last question. Okay, can we use this method to polarize more protons by using larger dose of chemicals? What will be the maximum dose and how much polarization could be reached? So the limiting factor is going to be sort of how much catalyst. So if you have a fixed amount of catalyst, you can increase the concentration of the thing you're trying to hyperpolarize, but you get diminishing returns at some point, because there's just, if there's so much of the target molecule in solution, it doesn't interact much with the catalyst, and any hyperpolarization you create decays because of relaxation before you can make any more. Now, of course, you could just increase the concentration of the catalyst, and that will work up to a certain point. But at a certain point, if you've got a high concentration of catalyst, the catalyst molecules might start interacting with each other, and then you'll get aggregates, maybe form dimers and things like that. And so, there is a fundamental limit to how much you could do. Now, if you just created a huge vat of it, you may be able to make a lot, but I don't think, if you're thinking about in terms of concentration, there's probably concentration limits
to how much you can hyperpolarize.
Thank you. Yeah, I also guess that dissolving of parahydrogen is a crucial thing, right?
Yeah, so that, I mean, that has a lot to do with what solvent you choose, what pressures you work at, and it's sort of an interesting situation because you're trying to replace hydrogen with parahydrogen. You're not working against a concentration gradient because you're not consuming the hydrogen. And so actually, we, instead of bubbling continuously, we stop and start bubbling between experiments because we find that by outgassing and then repressurizing, we get much better polarization levels. Otherwise, you just reach a much lower steady state because you're not properly replacing the parahydrogen, the used hydrogen in solution.